So yes, we're going to play with the difference quotient today. And some of you might remember that from algebra. And again, we're just going to do it the algebra style, the way you did it in college algebra. We're not going to do the actual derivative, but I might mention what's going on. But this is very important concept, and when you take your Calc 1 course, you know, you'll be doing a lot of that before the first exam. So given a function f, we define a difference quotient by this formula, f of x plus h minus f of x over h. So you all remember that from algebra, right? This little thing. You play with that in algebra. Now, where it comes from, I'll mention it just briefly, what this formula is all about. So let's say you have some kind of a function, whatever, you know, here's some function f, okay? And let's say you have a point on this function. We'll say this is some x value. So therefore, this thing right here is f of x. And what you want to do, you want to find the slope of a tangent line to the graph of this function at that point. So this is what I mean by tangent line. It just touches the graph at one point. So what's the problem with finding a slope of a tangent line? What's the problem with finding the slope of that line? We don't have a second point. You're exactly right. When you're looking for the slope of the line, you usually expect to do something like that. Change in y over change in x, right? So we don't have a second point. We cannot do the slope. So to fix this problem, well, let's make up a second point. And let's take our second point, you know, pretty close to the original x. Let's take that point. And let's say this point is h units away from x, which is going to move. Whatever the h is, we're going to move forward h units. So if that's what we're doing, what is this point on the x-axis? If this is x, and then we'll take h more steps, where we're going to end up? X plus h. So if this is x plus h, so if I go back up to the function, well, what is the y value? Anyone? F of x plus h. Right? So this is the second point here is x plus h f of x plus h. So we're actually going to look at this line right here, at the red line. And we're going to go ahead and find the slope of that red line. So we have 2 points now. So change in y. So this is my change in y, right? So it's f of x plus h minus f of x.
Would that red line be considered?
No, that would be considered a secant line. So the line that crosses at 2 points is called the secant line. The one that just touches is called the tangent line. It's a good question. But anyway, so you see how this numerator is just changing y based on this little diagram? Well, what is change in x? What is this distance? H. So h is in the denominator. So this is change in y or change in x. So this difference quotient formula is nothing but a, slope of a line. So now, this is as far as we went in college algebra. This is as far as we're going to go here. When you're going to take your actual calculus course, you're going to say, well, why are we doing the secant line when we want a tangent line? So what you're going to do, you're going to shrink the h. You're going to make h basically 0. So as smaller you get, as smaller you make your h, the smaller this distance becomes between x and x plus h. So the closer the secant line gets to a tangent line. So this is, you kind of start approximating the slope of a tangent line by taking a bunch of secant lines and see what you get. So eventually, h will be virtually 0. So when we do our simplification, that's why we want to cancel that h in the denominator. Because you cannot just go put 0 for h. It will cause a lot of trouble. Okay? So for now, we're just going to set those things up and then simplify till that original h goes away. And this is the hard part. And this is the algebra pre-calculus part. The calculus part will be the easiest thing ever when you're going to do next semester, is when you just ignore the h, oh, let it be 0. So here's the calculus, done. Okay? The algebra is the hard part. So let's do a few examples where we actually, what we mean by computing the difference quotient. And again, it should be pretty fresh from college algebra. So find the difference quotient of these functions. So here's my first example. F of x equals negative x squared plus 3x plus 4. So the biggest, half of your success here is the actual setup of the difference quotient. So we have the formula. Now we just need to set it up. So from whatever we did on Wednesday, remember the whole smiley face thing. Whatever goes in the little parentheses after the name of the function replaces the variable. Right? So, because there are really 3 parts in this formula. There's f of x plus h. That's the one part. There's f of x is another part. And then there's h is the third part. So first, let's just do f of x plus h. So this thing tells me to put x plus h for every x in my original function. So this becomes negative of x plus h squared plus 3 times x plus h plus 4. So this right here is f of x plus h. Then the formula tells me subtract f of x, subtract the original function. So I have to be very careful. So I'm going to put a minus and a set of parentheses. So this way I'll make sure that the negative distributes throughout the function. Or you can change all the signs, but it's harder to keep track of. And everything over h. So this thing right here is f of x. Questions on how we set that up? Does that make sense? Where all that came from? Given the function, given the formula. Okay, so the rest is algebra. Now remember, the goal is to kill that original h from the denominator. So now we need to open up all the parentheses, combine like terms. You can all do it your own way, but I know when you square a sum, you get x squared plus 2xh plus h squared. With the minus up front, so I'm going to distribute the minus, so it's negative x squared minus 2xh minus h squared. So that's squaring and distributing a negative at once, then plus 3x plus 3h plus 4. Then distribute the negative, so it's plus x squared minus 3x minus 4. Yeah, so a bunch of stuff cancels. X squared cancel, 3x's, and 4's. So everything went away. Now, if you notice, well, there's at least one h in each term in the numerator, right? So we can factor out that h. I can factor out the h, and it will give me negative 2x minus h plus 3 over h. Right? So there's whatever's left in the numerator has at least one h in it, so we can cross out the h's. And this is the second you cross out that original h, we're done. So negative 2x minus h plus 3. Okay? So we're done. You were done at this step in college algebra. We're finished at this step in pre-calc. In calc 1, you'll have one more step to take. You say, let h equal 0, so you're left with negative 2x plus 3. So that's calculus. The easiest step in this whole process. Okay? Questions on this? So actually, again, in calculus, you'll say, well, if h equals 0, so you're left with negative 2x plus 3. So now, whatever the graph of this function is, which is some parabola, that expression, negative 2x plus 3, will tell you the slope of a tangent line to that parabola at any given x. So let's say if x equals 1, you plug in 1, negative 2 plus 3, 1. So that means slope is 1. If you plug in x equals negative 4, you'll get 11. So the slope is 11 at that point. So it's kind of neat. It gives you the slope of a tangent line at any point on the graph. Okay? So if you're sliding on that graph, you'll know how fast you're going at any point on that graph. That's what the slope of a tangent line will tell you in Calc 1. So that's kind of cool. But anyways, for now, we just need to compute that. Okay? So, a few more of these. 3 over 2x plus 1. So again, we want to compute the difference quotient. So that's given by the formula f of x plus h minus f of x all over h. So if I set this up, it is 3 over 2 times x plus h plus 1. That's f of x plus h. Minus the original 3 over 2x plus 1 all over h. Does the setup make sense? Just like before, you have first thing is the f of x plus h, then f of x over h. So we need to simplify this thing, and this is what we call a complex fraction, that it has fractions within fractions. And the easiest way to do that is to find the LCD for all little fractions. So it's really just these two expressions in the numerator. What is the LCD for these two fractions? Yeah, because they're different. Yeah, because they're different. They look similar, but they're not. Just like, 7 looks similar to 5, the LCD is still 7 times 5. Silly example, but it's kind of the same thing. So yes, the LCD, you need both of these. 2 times x plus h plus 1 times 2x plus 1. So what we're going to do with that LCD, we'll multiply the numerator by the LCD and the denominator by the LCD. So this is the trick we use to simplify complex fractions. Actually, it works pretty well. We did something similar maybe on Monday, when we were, on Monday probably, when we were solving equations that had fractions, when we multiply both sides by the LCD and then you distribute and cancel all denominators. This is the same thing. Because look what happens if I take this expression and I multiply this expression by the first fraction. What will cancel? Yeah, the entire denominator will cancel, right? And what is left? 3 times, right, 6x plus 3, or 3 times 2x plus 1, right? So whatever's left, 3 and the second factor, so 3 times 2x plus 1. Minus, we do the same thing again, 2x plus 1 cancels, right? And we're left with 3 times 2 times x plus h plus 1, like that. Right? All over. Now here is just a straight up product, nothing fancy going on. Nothing cancels, so that's just h times 2x plus h plus 1, 2x plus 1. Because again, remember that we're after this h right here. This is the h that we're after. That's what we want to kill. We might end up with a new h in the denominator, but it won't be a troublemaker. Because again, remember, we eventually want to set h to 0. Right now, we cannot do that. So we'll make denominator 0. But in the future, in a few steps, we'll be able to do that without getting 0 in the denominator. So anyways, open up. Just don't mess with the denominator. Mess with the numerator. Open up all the parentheses. So it's 6x plus 3 minus 6 times x plus h minus 3. See what I did? I just distributed negative 3 like that. And then we'll distribute negative 6. So 3's cancel. Distribute negative 6. We'll get 6x minus 6x minus 6h all over h times 2x plus h plus 1, 2x plus 1. So 6x cancels with 6x. So we're down to just negative 6h over all that junk. And now we can cancel that h. So when you cancel that h, we're done. So we end up with negative 6 over 2 times x plus h plus 1, 2x plus 1. Okay? So then in calculus, you'll say, well, let h equal 0. So then you'll have just 2x plus 1, 2x plus 1 in the denominator. So it's 2x plus 1 squared. So that's the only thing you're going to add to this problem. Is this okay? So one more, the square root. We usually want to do a square root example. And then we're done with that. We're just going to do it on the homework. So again, computing the difference quotient, f of x plus h minus f of x over h, provided that our function is the square root of x. So when we set this up, we'll end up with the square root of x plus h minus the square root of x over h. So how do we simplify something like that?
Square root of x plus h is also square root of x plus h squared.
No. Well, few problems with that. By squaring the whole thing, first of all, it changes the problem, right? If I take 1/2 and I square that, it's 1/4 now. So it's not the same as 1/2. And just by squaring it still won't get rid of all the radicals. But there is a trick that we definitely talked about in college algebra. Because you kind of want to end up with, let me use my magic pen, you want to end up with something like that. That's what you want, right? Does anybody remember? What I want to do, I want to utilize this formula. This is how you artificially square items. Because what I have right now is something minus something, right? Conjugate, right. But if I multiply by the conjugate, I'll get little squares. This is what I want. So if I multiply the numerator by the conjugate, square root of x plus h plus the square root of x, I will have to multiply the denominator by the square root of x plus h plus the square root of x. So this will utilize the difference of squares formula. We'll get rid of the square roots in the numerator, and good things might happen. So by the difference of squares formula, we end up with the square root of x plus h squared minus the square root of x squared over h times the square root of x plus h plus the square root of x. So this way, we actually get rid of the square roots in the numerator, and we're not changing the original problem, since we multiplied by 1. So we're ending up with x plus h minus x over h times the square root of x plus h plus the square root of x. So first, the x's will cancel, and we're down to just h over h times the square root of x plus h plus the square root of x. And then h's cancel. And we're done. The original h is gone. Now there's no problem by putting 0 for the h. You're going to end up with 1 over 2 square root of x. But, so that's the calculus step, the easiest step. Isn't this fun? Yeah? Good. That's the final answer, yeah? Because there's, again, we're after the original h. When you just got rid of it, done. Nothing else to do. Okay, good. So this is your difference quotient. Now I'm going to talk about graphs. Again, it's a review of algebra. We're going to give you, family of functions that you need to know how to graph really fast. Like you need to know your parabolas and absolute values. Then I'm going to talk about symmetry. We're going to talk about shifting, left, right, up, down, all that good stuff. So again, it's a quick review of algebra. Because, well, first of all, we're supposed to review algebra in pre-calc. And we'll need that for future in this class, so it's important that we talk about it. So graphs. So basic shapes. So these are the shapes that you need to know. You need to know your parabola. So this is some f of x equals x squared. So all know the graph of the quadratic. So no matter what a quadratic function is, you're going to end up with some version of a parabola. The cubic. So the general shape of a cubic function. The square root function. Right, you're familiar with these shapes. I don't need to build a table of values to come up with that, right? You've seen those before. Just kind of, this is more of a refresher. The absolute value function. We already talked about that. The graph is a letter V. You have two lines, negative x, here's negative x, and positive x, meeting at the origin. One over x is something you should be familiar with. The graph of one over x is something like that. Six, your linear function, so f of x equals mx plus b. So these are the family of all linear functions. So depending on the slope, but we know b is the y-intercept, so the positive slope looks something like that, negative slope goes down, whatever. You know your linear functions. And then you have your exponential and logarithmic. So 7 exponential functions. In general, if a is greater than 1, the graph of the exponential function looks like that. Goes through 1. So this is for the case a is greater than 1. And logarithmic. So log base a of x. So let's say this is 1. So we'll have something like that. Good? You know these shapes? So the next one I want to talk about is symmetry. So some of the shapes possess a certain symmetry. And there are 3 major symmetries that we talk about in math. There's a symmetry around the x-axis, which literally means if you follow the graph along the x-axis, it overlaps itself. Now, we don't see much of that. Why? Just picture a graph that is symmetric around the x-axis. Will that be a graph of a function? No. So it wouldn't be a function, so we don't see much of that. But we do see things like, I'm going to use my magic pen here, things like, sideways parabola. That's not a function, but we can still talk about that at some point. Not much. And of course, your circles. If you look at the circle, that's centered. Okay, that's a magic pen. That's the silly thing. But so that's the x-axis. We don't see much of that. But there's also symmetry around the y-axis. The same thing. If you follow along the y-axis, it overlaps. So like this guy has a symmetry around the y-axis, right? What else has a symmetry around the y-axis? The absolute value has a symmetry around the y-axis. So that's another symmetry. And we also have a symmetry around the origin, which means, let's say if I take a point on the graph and then I rotate it around the origin. So let's say this point right here is some xy, then this point right there will be negative x, negative y. Just both signs change. So this type of symmetry we call symmetry around the origin. So the cubics have a symmetry around the origin. Is there anything else here has a symmetry around the origin? 1 over x, that's right. If I take 1 over x, if I take this part of the graph and I rotate around the origin 180 degrees, I'll get to the other side, so yes. So this is the symmetry around the origin. So it is easy to state the symmetry if you actually have a graph. If you look at the graph, then just, well, here's the symmetry. But a lot of times we don't see the graph, we just see the actual function, the definition of the function, and we're trying to sketch the graph, okay? So it's actually very helpful to sketch a graph if you know the symmetry of the graph that you're about to produce, right? I mean, if I know that the graph is going to be symmetric around the y-axis, all I really need is a half of that graph and then do the symmetry on the other half. Or if I know that the graph is symmetric around the origin, all I need is a half a graph and then use the symmetry to get the other half, okay? So there are special terms we use to describe functions that will possess these 2 symmetries. The functions that are symmetric around the y-axis, we call those even functions. And the functions that are symmetric around the origin, we'll call them odd functions. Okay, I'm going to write all that down. Now, unlike with integers, because integers either odd or even, with functions, you can be odd, even, or neither. If a function has no symmetry, like the square root of x, it's neither odd nor even. Okay? But if we take a look, let's say the parabola, right? So here's the symmetry around the y-axis. So the y value stays the same regardless of the sign of x, right? These 2 points, this one has a positive x value, this one has a negative x value, but the y value stays the same, right? So that's basically a definition of even functions. It doesn't matter whether x is odd or even, the result will be the same. So here's a definition. So definition of even functions. A function f is an even function if and only if f of negative x equals f of x for all x's in the domain of f. Okay? Because again, by looking at the graphs, doesn't matter x positive or negative, the value of the function stays the same. So even functions are symmetric with respect to the y-axis. So the odd functions, these are the ones that are symmetric around the origin. So here it says, if I change the sign of x, the sign of y will also change. Okay? So that means f of negative x equals negative f of x. So that's the definition of an odd function. So a function f is an odd function if f of negative x equals negative f of x for all x's in the domain of f. So odd functions are symmetric with respect to the origin. Is that okay? So again, we talked about this in algebra kind of briefly. It comes back again Because eventually we're going to talk about trigonometric functions, and they'll have those symmetries. Well, actually, some of the trigonometric functions are going to be even, some trigonometric functions are going to be odd, and that will help us actually a lot. It will be more useful than it is in college algebra, actually. And then when you actually be in calculus, this notion comes back again from a different angle, and it will be extremely useful there. It'll make your life a lot quicker. I mean, sorry, that's you don't want that to happen, right? But the work you do will go much quicker. If, let's say, you know the function is odd, good things will happen. But anyway, so how do we figure out whether the function is odd or even? So here are some examples. Determine whether function is odd, even, or neither. So here's an example. Let's say I have a function j of x equals x squared minus x over 100 minus 1. Okay, so I want to determine whether this function is odd, even, or neither. So the way we do that, I mean, our definitions for both functions, for both odd or even, they start at the same place, f of negative x. Okay? So that's what I want to do. I want to start computing f of negative x. If that negative sign somehow disappears and I'm back to where I've started, then I know the function is even. If not, then the easiest thing to do is to actually compute negative f of x separately and then just compare. This is what I got for f of negative x. This is what I get for negative f of x. Are they the same? If there are, then you get an odd function. If no, so it's not odd, not even, so it's neither. Okay? So let's try that. But always we're going to start with plugging negative x in for x. So that becomes negative x quantity squared minus negative x over 100 minus 1. Is that okay? So simplify this a little bit. That becomes x squared plus x over 100 minus 1. Is this the same as the original function? Right? The sign of the x over 100 changed. So it's not the same as the original, not equal to j of x, so the conclusion is it's not even, right? Because that sign changed. So it could still be odd, so let's try computing negative j of x, see whether this is the same as j of negative x. So all I have to do is just to change every sign in my original function, so it becomes negative x squared plus x over 100 plus 1. Is that the same as what we got above? No. So it is not equal to j of negative x, so not odd. So the function is neither odd nor even. So it's just some weird function. There's just some parabola that sits somewhere but does not have any one of those two symmetries. Is that okay? Here's another example. H of x equals 5x over 2 minus x cubed. So the same equation is a function odd, even, or neither. So first, again, we'll start by computing h of negative x. So I'm going to replace each x with a negative x, so that becomes 5 times negative x over 2 minus negative x cubed. So this is negative 5x over 2 plus x cubed. Right? Hmm? Well, is that the same as the original? Well, is it the same as the negative of the original? That's the thing. But look, do you see that it's not the same as the original? I can actually do this by the properties of fractions. I can take the negative from the numerator, since this negative is applied to the entire numerator. And I can just place that negative in front of the function like so. Well, does it? So is this the same as the original function? Well, no, not really. So it's not the same. The whole thing is not equal to the original function. And if you just ignore the negative, that's not equal to the original function. So it's neither. It's neither odd nor even. You can actually, if you're able to pull a negative like that out, you can actually stop and say, well, it's not the same. It's not the same as the original, and it's not the same as negative of the original. So this is another example of neither. But if I change this problem just a little bit, if I look at this function, so it's 5x and then 2x minus x cubed. I can probably reduce this thing, right? I can factor out an x and simplify, but let's not. I mean, I should, but just for the sake of showing you the mess, right? Because I can reduce everything by x. But if I just try this, if I just do f of negative x, see what happens. It's 5 times negative x over 2 times negative x minus negative x cubed. Right? Just put negative x for every x. So now if I simplify this, this is negative 5x over negative 2x plus x cubed. Right? So looks like a big mess right now. But you see how every single sign changed? Every single sign changed in the numerator, and every single sign changed in the denominator, right? That means I should be able to factor out the negatives and reduce them. See what happens if I pull out a negative out of the denominator. If I pull out a negative out of the denominator, it gives me 2x minus x cubed, like that, right? And if I cross out the negatives, that's the same as the original, right? So it's even. Right? Of course, it would be easier if we just cancel, if we reduce by x. It would be a lot simpler. If we did that first, if we said, well, this function is 5x over x times 2 minus x squared, so x is canceled, and you're down to 5 over 2 minus x squared. So then it should be pretty clear. It doesn't matter whether x is positive or negative. We're going to square it. You always get back to this place. And that's how you should have worked this problem. Reduce first and then do that. Okay? Good. Good stuff. Now, again, a quick review. So any questions on odd even stuff? I mean, does that look familiar? You've done that in algebra? I know we did. So it'll be on your homework. You'll practice with that. Now, transformations, translations, shifts, flips, and so forth. All that fun stuff. We usually call it the acrobatics of functions. Kind of a cute way to call that process. So I'm going to list a whole bunch of little rules that you've done in college algebra. For all of them, the graph of the function is known, and C is some positive number. So we're going to try to sketch the following functions. Y equals f of x plus c. So basically what I'm talking about, you know the graph of f. C is some positive constant. What happens to the graph of f if you add a constant to it? Where's the graph going to go? Up? Down? So, well, what am I messing with here? Just, you know, because we're messing with the y-axis. You're increasing every y value by some number. So if every y value gets a number added to it, where is everything going to go? Up. So this whole thing shifts up. So example of this, I'm going to do a quick example here. Let's say f of x equals x squared plus 2. Okay? You know the graph of the parabola, plus 2 shifts everything 2 units upward. So the graph of that is something like this, so going through 2. Is that okay? If I subtract a number, so I'm reducing every y value, where's the graph going to go? Down. So if I had x squared minus 2, I would have a parabola that crosses the y-axis at negative 2. Is that okay? So these are my vertical shifts. Because again, pay attention to what this notation means. It means that I'm adding something to all the y values. So if I'm adding to y values, it goes up. If I'm subtracting from y values, it goes down. Which takes us to this point. F of x plus c. So again, c is a positive number. So where's the graph of the function going to go? Left, right? Left. Because now we're messing with the x values, right? So shift is horizontal. So that's going to be a general pattern here. If you're messing on the outside, the changes happen along the vertical axis. If you mess on the inside, the change happens along the horizontal axis, because that's what you're messing with. So yeah, the shift is to the left. So again, example of this would be something like x plus 2 squared, right? The graph, because if you think about this, what is the x-intercept? What does x has to be in order for this function to touch the x-axis? So it has to be negative 2, right? X has to be negative 2, so this is why it actually sits at negative 2 like that, okay? So shift to the left. So if I subtract something, on the inside, y equals f of x minus c, it shifts to the right. Okay? All right. So we have vertical shifts, horizontal shifts. Now let's do the flips. Y equals negative f of x. So if I place a negative in front of the function, what happens to the graph of that function? Right, it flex over the x-axis. Because again, from what I said earlier, we're messing on the outside. We're messing with the function, right? So that means we're messing with the y values. So all it says, change the sign of your y value. So the positive y becomes negative and the negative y becomes positive. So the flip occurs around the x-axis. So we're going to flip vertically. So flip around the x-axis or reflect. At the same time, if I put a negative on the inside, so I'm messing with the x values now. So all the x's change their sign. Positive x becomes negative, and negative x becomes positive, so the flip occurs around the y-axis. So it's this flip. So for example, I want to sketch something like this. So it's negative x plus 1 squared minus 3. How do we sketch this thing? What graph are we messing with? Parabola? What's going to happen to that parabola? Left, up 3, down 3. Okay, so it's an upside down parabola living there, right? Technically, you're supposed to go 1 to the left, flip, and then down. Because if you go 1 to the left, 3 down, and then flip, you'll end up over here. I mean, if you really do the flip. Because the reason for that, you just follow the order of operation. Parentheses, multiplication, subtraction. Okay? So you get there. All right. So these are the 6 basics. You all know and love these 6 transformations. I have 4 more. Okay? So here's the 7th. Let C be greater than 1. So C is positive and bigger than 1. So I'm trying to sketch the graph of C times f of x. So I'm messing on the outside. I'm messing with the function. So I'm messing with the y values. So if C is bigger than 1, let's say if C is 2, I'm multiplying all the values by 2. So the graph, all the y values, get doubled. So the graph stretches vertically. So stretch the graph but if C is less than 1, but still positive, so let's say C is 1/2, that means I'm dividing all y values by 2, so all values decrease by half, so we're going to shrink the graph vertically. by a factor of c, and here is also by a factor of c. So, how are you doing so far? Are these familiar? So again, there are two more, there are 10 of them. But there's a quick way to remember all of them, really, if you just understand the pattern. If you mess on the outside, the changes happen along the y-axis, okay? And when changes happen along the y-axis, they're very intuitive. You add, it adds. You subtract, it decreases. You multiply by something big, everything gets bigger, stretches. You multiply by something small, everything gets smaller, okay? Now, and here's the big thing. When you mess on the inside, you mess with the x-axis, and all the results are counterintuitive. You add, you move left. You subtract, you move right. Right? This is kind of counterintuitive, right? So same thing will happen here. If you multiply by bigger than 1, things will actually compress. And if you multiply by less than 1, things will actually stretch. And this compressed stretch will become really important to us in this class because we're going to have those wavy looking functions. So the rule number 9, again, if c is greater than 1, then to sketch f of cx, so now we're messing on the inside, we're messing with the x. So the change occurs along the horizontal axis. Everything will shrink or compress. Compress horizontally by a factor of c. And the 10th transformation, if c is between 0 and 1, so everything will stretch horizontally by a factor of c. Is that okay? So again, all we need to know is the pattern. Mess on the outside, changes are vertical and very intuitive. Change on the inside, changes are horizontal and counterintuitive. So if you remember that, you got them all. Okay? I want to do some fun examples with that. And again, we've done that in algebra.
I like how you just the counterintuitive thing. This part right here, the stretching and shrinking.
Yeah, but if you just remember whatever if it's vertical, then, whatever feels right is right. If it's horizontal, the opposite of what feels right is right. Which, right, isn't that opposite? You go bigger than 1, actually that's everything compressed. Well, good. I'm glad you like that. I'll give you a few more of those little words of wisdom. That's your tuition at work right there. So I'm going to draw a silly graph. Just going to make one up. Because again, with our family of functions, we cannot have a whole lot of fun. So I'm going to make up a function that has the following points. -1, -2, goes through the origin, then has a point 1, 1, and has a point 2, 3, and has a point 3, 0. So bam, 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 bam. Here's a function. Okay, this is f. So I want us to sketch y equals f of x plus 1, like that. Is that going to be a struggle? What do we have to do? Yeah. So all y values got 1 added to, right? So you can actually follow that guidelines. -1, -2 becomes -1, -1, right? 0, 0 becomes 0, 1. 1, 1 becomes 1, 2. 2, 3 becomes 2, 4. 3, 0 becomes 3, 1. So you can always reference those points and then again connect the dots. Here we go. Fun. So that wasn't bad. How about sketch y equals f of x minus 2? How would we accomplish that? So where am I going, left or right? Right. So every x increases by 2. So -1 becomes +1, right? 0 becomes 2. 1 becomes 3, right? 2 becomes 4. And 3 becomes 5. Kind of lost count there, not drawn to scale. But all I did, I just moved every point 1 unit to the right, 2 units to the right. Okay? Is that okay? How about this one? Y equals negative f of negative x. So two things happen. Yeah, it'll reflect over the x and the y. Yeah, flips in both directions. Yeah, so both signs change. -1, -2 becomes +1, +2, right? So let's try this. Is that the point? 0, 0 is 0, 0. You flip it all you want, it's still that point, right? 1, 1 becomes -1, -1, right? 2, 3 becomes -2, -3, right? 3, 0 becomes -3, 0. So something like that. So did 2 flips. And you will see problems like this in the homework where they'll give you like a squiggly thing like that, but you always have few reference points, so you just refer to them and then connect the dots, so easier that way. Okay? All right. I want to do a few more with this thing. I don't know what will come out of that copy. Oh, that's what I wanted. Where were the x's? We had, this was the, right, 0, 0, right? Kind of like that. No, 3. Look at that, see? Oops. It was almost perfect. Whoa, that's crooked. We can fix this. Okay, see, that's why I didn't need that. I'm just having fun right now. Okay. Good. I want to do this. Y equals 1/2 f of x. Messing on the outside. So what am I messing with? X's or y's? Y's. So all it says, divide every y value by 2. That's all it says, right? So -2 becomes -1. 0 is 0. 1 becomes 1/2. 3 becomes 1.5. 0 is 0. So something like that. So everything kind of got dropped by 1/2, right? These distances are the same any point you look at. Distance from the x to the graph and from the graph to the original, because we were halving it. If we were going 1/3, so everything would be like 2/3, 1/3, like that. Is that okay? I want to do this one. Y equals f of 1/2 of x. So it will stretch. So everything will double. If this is 1/2, and I have 1/3, everything will triple. So -1 would become -2, right? But the y value would be the same. Right? We're only messing with the x's. Now, origin doesn't move. Now let's see. 1, 2 will become 2, 2. 2, 3 will become 4, 3, right? And 3, 0 will become 6, 0. So everything doubles on the x-axis. So if I connect that, I'll get something like this. How's that? So if you have those reference points, it's really easy to do those graphs. So you see, and the key here, when we were messing with the y's, all the x's stayed the same to the original graph. The y's changed. When we're messing with the x's, all the y values stayed the same. Only x's changed. Okay? And of course, if we messed with both, then both would change. Well, good. That's all I wanted to show you today. Do you have any questions?
We're going to be doing this more, right?
Well, no.
Oh, we're not going to be doing like graphs.
Well, we'll be doing graphs in relation to new functions that we'll learn. So yeah, this will come up again. Now, as far as just messing with, our standard functions like that, we won't be. I mean, you'll see some of this, but not much. We'll discover a whole new family of functions, and then we'll apply all that stuff to it. But you'll do a nice little homework on this, just on the basics. So watch little videos, little tutorials if you get stuck. Take advantage of the learning tools available to you, and you'll be fine.